Welcome to the University of Michigan Dentistry Podcast Series, promoting oral health care worldwide.
Today we're going to consider Archwire materials and selections, and with us is Bill Proffitt, the chairman of the Department of Orthodontics at the University of North Carolina. Bill, thank you for coming today.
Well, it's a pleasure to come out to Michigan. I always like to see the opposition in person.
We're going to talk about the selection of the many types of archwires that are currently available today. And first of all, I want to talk about just appliances in general, about the difference between an 018-inch slot and an 022-inch slot. What's the history of that, and what relevance do you think that has today?
It has a lot of relevance, really. The 022 slot goes back to some engineering that Edward Angle did when he invented the edgewise appliance, and it had very much to do with the wire materials that he was going to use in developing that appliance. He had really no choice but to use gold for his arch wires. And the slot size then became a function of the properties of that material. What's really interesting is why the 022 slot survived when gold was supplanted by stainless steel as an archwire material.
Why did that happen?
Well, at about that time, Edward Angle assumed that the orthodontist would always fill the bracket slot with the arch wire. He didn't anticipate sliding teeth along arch wires. If you never created an extraction space, of course, there'd be no reason to slide teeth. And so almost by chance, just as extraction therapy was introduced into edgewise orthodontics and undersized wires became important, undersized steel wires became available. And so for a time, in fact, even as recently as I was trained, somewhat less than 100 years ago, we had gold brackets still, but we were putting steel wires into those gold brackets. The interesting thing is that if you use the 022 slot, you are really almost making a statement that sliding teeth along the arch wire is important to you. Now, if you want to use the appliance largely as Edward Angle did, so that most of the time you will fill up the bracket slot with the arch wire, the engineering analysis says that if you reduce the slot size to 18 thousandths of an inch instead of 22, then you could make a steel wire of 17 by 25 dimension that would have about the same properties as Edward Angle's 22 by 28 arch wire.
But that being his was a gold wire, though,
Yeah,
right?
and
Okay.
So at this point, about 55% of orthodontists use 22 slot and about 45% use 18 slot. I always have a good time asking people if they know why they're using one or the other of those slots, because it really does have an implication as to how you're going to use the appliance.
Now, it seems to me that when I've heard you talk before on this subject, you gave the first Gerback lecture here at Michigan, and your topic was somewhat along the same lines we're talking about today. You said that you needed about 2 1,000ths of an inch clearance in the slot to facilitate sliding mechanics, so that if you had an 018 slot, you'd use an 016. If you had an 022 slot, you'd use an 020. Is that still true, or has that been modified?
I think that's still true. If you don't have at least a nominal 2,000ths of an inch clearance, you're going to have a problem when the bracket slides relative to the arch wire. The companies that make materials for orthodontists are pretty smart about that. They know that orthodontists usually don't want things to fit too tightly. And so when they machine brackets, they always machine them, their tolerances of course, so that the one you get is at least as big as they said it was. That is, a 22 slot bracket will never be less than that. It might be more.
Mm-hmm.
And when they make arch wires, they do just the reverse. If they sell you an 018 wire, it'll never be bigger than that. It might be smaller, and often is a little bit. So it's almost as if there's another 1,000th of an inch beyond the nominal clearance. A 16 wire and an 18 bracket usually gives you closer to 3,000ths clearance, and that's plenty, really, for sliding.
If you were a young orthodontist going out today, what would influence your decision regarding going with an 018 slot or an 022 slot?
From my perspective, a few years ago, the 18-slot bracket had lots of advantages over the 22-slot bracket, and the developments in archwires in recent years have in many ways closed that gap and made the two more comparable once again. The disadvantage of the 22-slot bracket in the steel era was it made it very difficult to finish with the archwire in the way that Edward Angle thought you ought to use the edgewise appliance. If you put a full dimension steel wire in a 22-slot bracket, that wire is just too stiff to have much range at all in moving the teeth, and the forces it delivers are much too heavy. And so if you use steel wires with a 22-slot appliance, you're almost forced to use auxiliaries for finishing and those kinds of things. In contrast, with the 18-slot, you can finish very nicely with a steel wire. But you don't have to use steel wires anymore, and especially if you're a 22-slot person, you probably shouldn't. You really need the titanium wires in order to finish your cases. Now that they're available, some of the advantage that finishing with steel wires in 18-slot is not quite as great as it used to be.
Now, you've mentioned so far a number of different materials for archwires, and I think we should probably go through those now. Obviously, the first archwire material was gold, and you say that was it for a long, long time, right?
Yeah, nothing but precious metal really could stand up in the mouth until stainless steel was developed. The gold wires weren't really pure gold, of course. That would be too soft. They were gold alloys of various types, and in fact, putting some platinum and other precious metals in there helped. But you had all of the disadvantages that go with precious metal. You know, it was expensive, didn't have very good spring properties, all those kinds of things. So the introduction of stainless steel was a tremendous boon to orthodontists.
Now, you were trained at University of Washington about, what, 1960, somewhere in there?
I finished at Washington in '63.
Okay. And you were still, at that time, were using stainless steel wires and gold brackets, you said?
At that time, we used a mixture of steel bands and brackets and gold bands and brackets, but most of the cases still had gold bands and brackets. But we used steel wires because of their better performance.
When did stainless steel become available?
Really in the aftermath of World War II. It was introduced prior to World War II, but it wasn't used much until the 1950s, and then it very rapidly displaced gold.
Now, what would be the properties of stainless steel wire that everyone is so familiar with? What are the...
Well, essentially, stainless steel doesn't corrode in the mouth, and that, of course, is the first requirement, and that's really the key one. But then it has excellent spring properties. Stainless steel isn't any springier than any other kind of steel. But you've got the spring properties combined with the ability to stand up within the mouth. You couldn't make an orthodontic something out of white spring steel because it'd be rusted and corroded in days. Stainless steel survives, and yet it's very strong compared to precious metal, and it has beautiful spring properties compared to precious metal, immensely better.
In the second edition of your book, you have a number of diagrams that relate to this subject, one of which is the force deflection diagram. Could you go through that with me and explain exactly the parts of this?
Sure. We can take a look at one of the diagrams that is in the book. If we look at this drawing, what we're doing is plotting deflection on the x-axis against force on the y-axis. And if you do that with a material like steel or gold or whatever, you will get a curve that has a linear portion, and then at a certain point it will deviate from linearity. The wire will begin to bend over. It will reach a point at which it can't take anymore and will actually decrease the amount of force, and then there's a point at which it will break. The difference between steel and gold, for instance, is in the slope of that curve. A gold wire would be out in this direction. It wouldn't be nearly as strong as stainless steel. Might not be quite as stiff either, actually, but it just wouldn't have as good clinical properties on a diagram of that type.
What does the term yield point mean?
Oh, yield point is the point at which there is enough of a deviation from linearity that you can actually measure it, and that's an important thing in determining the strength of the material. That's the point at which there's a 0.1% deviation from linearity. If you take the wire to its yield point, it won't quite spring back to where it started from.
So that everything up to the proportional limit point, you'll have 100% spring back?
That's right.
And then what is the arbitrary clinical loading point? What does that mean?
Well, that you can use clinically things that are outside this linear range. If, for instance, Jim McNamara installs a spring and he bends the wire to the point that it's partially permanently deformed, it'll spring back along this line that's parallel with the original one, and you'll end up back at this point here. And so then you have a spring back along the x-axis that's the useful range of the wire from that point of loading back to where it ended up.
Given that diagram, what are the properties you think are most important for people to remember about this?
You can really see the three key things on a force deflection diagram. The strength of the wire is shown by the y-axis. Further up you go on the y-axis, the stronger the wire. The range of the wire, how far it can bend and how much then it can move a tooth before you have to reactivate it, is the distance along the x-axis. That's either the range or the spring back, depending on how far you bend it. And the slope of the line, how flat it is or how steep vertically, gives you the stiffness or springiness. Those are the same thing. Springiness is just the inverse of stiffness.
What is the relationship between the diameter of a round wire, obviously 016, 018, 020, and so on, and also what is the relationship between a round wire and a rectangular wire with regard to these properties?
What you have to remember is that as the diameter of a wire increases, the properties change really quite dramatically, and they don't all change the same. The springiness, for instance, is a fourth power function of the change in the diameter, so that as a wire gets bigger, it gets stiffer or loses springiness really fast. Now, it also gets stronger, and it has less range. But those are different functions, and students really do need to know those things.
Can you give me an example, a clinical example, of like an 016 versus an 018 or something like that sort?
Okay.
Or any other convenient example you might
Okay.
know?
Well, I don't know that I can do the arithmetic in my head, but if you wanted to know how much stiffer an 018 wire is than an 016 wire, it would be 18 over 16 to the fourth power. And my guess is it would come out that the 018 wire is twice as stiff as an 016 wire because of that power function of the ratio of the diameters.
Now, obviously, this is of significance with regard to stainless steel. And as we'll see later, it's not as critical with regard to some of the other wires. Is that right?
Well, those ratios hold if a wire obeys Hooke's law of elastic materials. If it's an elastic material, if it has a force deflection curve that looks like the one we just showed, then it wouldn't really matter. In other words, whatever the material, the 018 would be almost twice as stiff as the 016. But we're going to run into some things that don't obey Hooke's law, that aren't elastic materials in the classic sense.
Okay. Now, the third wire in this sequence, which I have a particular affinity for, is the chrome cobalt wires. And of course, with my use of utility arches and alloy wire and azurloy wire and things of that sort, where does this fit into the scheme of what we've talked about thus far?
Well, Dr. McNamara always did like to go first class, and if it costs more, it must be better, right, Jim? and so the chrome cobalt alloys were originally developed as watch springs by the Elgin Watch Company, and that's why to this day those are still called alloy. The chrome cobalt material, although it's quite different physically from stainless steel, that is, it isn't steel, nevertheless has almost identical spring properties, so that a spring made out of chrome cobalt and a spring made out of stainless steel will perform almost identically. The advantage of the chrome cobalt materials is that they're easier to bend and form, and they are supplied so that they can be heat treated after being formed, And so it's not that they perform better in the mouth, it is that they may perform better in the office. That is, they're easier for you to use when you're making whatever you want to make. That's
now,
their advantage.
You know, one of the things that Bob Ricketts in the bioprogressive technique in a lot of the utility arches uses chrome cobalt in an unheat treated form. And so you can, it's a much softer wire. And
Yeah,
it seems
that's
to
probably the worst of both worlds. You know, you paid extra for a property you're not using.
Because it seems that the force levels that I use intraorally work out very nicely using unheat treated material.
You know, and so presumably if you used a smaller size of steel wire, you could get the same thing
Could
for
be,
less
could be.
cost.
What's the relationship between stainless steel and chrome cobalt? I mean, do you have any idea about the difference between a stainless steel wire, presumably unheat treated,
Yeah.
and then an unheat treated chrome cobalt? Any idea about that?
Well, truly, you know, the performance of steel and chrome cobalt wires is extremely similar. The spring properties of both steel and chrome cobalt can be manipulated by the heat treatment of the wire. It's difficult for the orthodontist to take advantage of heat treatment effects with steel wires in the office, and it's easier with the chrome cobalt.
Okay.
But in all honesty, I think that the chrome cobalt wires don't have much advantage anymore as they did when they were almost the only alternative to steel, because now you can do better tricks with titanium wires than you could with chrome cobalt.
Let's move into the issue of titanium, both beta titanium and nickel titanium wires. When did this development start to take place? What time in history?
Well, it's really interesting, I think, to consider the relationship of what orthodontists do to the aerospace industry. You could say, if you wanted to, that orthodontic technology trails aerospace technology by 10 to 15 years. Back in the 1960s, when spacecraft were just a dream, it was obvious that you had to have antennas for spacecraft, and so what you wanted out in space was a great big antenna, but it wanted to be stuffed in a little tiny package to get it shot up into space. And so the Naval Ordnance Laboratory, I used to live right next door to it in Bethesda, Maryland in my days of helping Uncle Sam at his request. The Naval Ordnance Laboratory developed nickel titanium alloys, which were chosen for their spring properties. The idea was to have something that you could crumple into a little ball, and then spring in space, you would have a great big antenna. Those alloys were and still are the springiest things ever made, and so almost immediately orthodontists began to dream of using nickel titanium alloys for orthodontic purposes.
Now, we've talked about beta titanium and nickel titanium. Do you want to distinguish between the two?
Nickel titanium is about 60% titanium and 40% nickel.
Okay.
Beta titanium is almost pure titanium. It's maybe 97% titanium, something like that.
In the beta titanium, what's a good example of an orthodontic wire made out of that?
There's really only one, the one that Ormco sells as TMA, that's titanium molybdenum alloy. Maybe it's 87% titanium. It's got some molybdenum in it, but it's pretty close to pure titanium, whereas nickel titanium has lots of nickel in it.
Now, beta titanium has properties that are more closely related to stainless steel than nickel titanium. Is that correct?
Yes, beta titanium isn't as springy as nickel titanium, but it's springier. It has better properties in a number of ways than stainless steel, particularly if you wanted to fill the bracket slot with a 22-slot appliance and you made your wire out of beta titanium, you'd really be closer to gold from that point of view. So you could say it's an intermediate between stainless steel and gold.
Now, one of the things that stainless steel has and chrome cobalt has is good formability.
That's true.
And I think that's pretty much true of the beta titanium as well.
Yeah, beta titanium is pretty hard to bend, and so it really isn't as formable, but you can bend it. The nickel titanium wires are very difficult to form. What the manufacturer gives you is pretty much what you're going to have to live with as the orthodontist. You can't bend it and shape it very much, and that's one of the disadvantages of those things.
Now, you could undoubtedly intersperse the three wires that we've talked about of stainless steel, chrome cobalt, and beta titanium in certain instances, I suspect, because you can put one way or another, first, second, third order bends and things of that sort in, right?
And I gather that even though I'm your guest today, I don't necessarily have to appeal to your prejudices. I'm going to tell you that there are three big classes of wires.
Okay.
There's stainless steel and its close cousin, chrome cobalt or alloy.
Okay.
And then there's something that's rather different, the beta titanium or TMA, titanium molybdenum. And then there's something again that's very different, and that's nickel titanium.
Right.
So I would say that the chrome cobalt and stainless steel are so close you can lump them together.
Okay. Now, do you want to, let's move on to nickel titanium then.
Okay.
Now, nickel titanium has some chemical properties or physical properties that are very different than anything we've talked about before.
What the smart boys at the Naval Ordnance Laboratory were doing with nickel titanium was taking advantage of its transition between two phases. People who go to Dome School got taught once upon a time about martensitic and austenitic forms of materials, and there were phase diagrams and all this stuff. And that probably doesn't mean very much to orthodontists till you get to the nickel titanium materials. Nickel titanium undergoes a transition from a martensitic form to an austenitic form as a function of temperature. And its properties when it's martensite can be quite different from its properties when it's austenite. And so for a spacecraft antenna, the trick was, in fact, to have it in one form when it was warm on Earth, and you crammed it into the spacecraft, and it's cold in outer space, and so the material that arrived in outer space would be very different from the material that they had on Earth. Temperature transition nickel titanium materials have been only marginally useful in orthodontics. And so the original nickel titanium material, which was called nitinol, because NOL, Naval Ordnance Laboratory, is a martensitic nickel titanium. And it behaves just like all the other wires on one of those diagrams. It's an elastic material. It follows Hooke's law. It's just a very springy elastic material. But not so many years ago, it became possible to produce a nickel titanium material that would undergo a transition from martensite to austenite at room temperature. And the transition could be induced by stress. And that had the interesting effect that when you bent the stuff, it would literally turn into something else while you were bending it. What you had when you tied it into the bracket was a different material from the one you put in the patient's mouth. It's the closest thing to magic we've ever had in orthodontics, this stress-induced phase transformation. And so that allowed the production of what are called super-elastic materials. The word super is so overused that people think, so it's super, a big bloody deal. You know, in this case, it is super. You know, these materials don't follow Hooke's law.
Now, in your book, you have a diagram that talks about this transition. You want to discuss that?
Yeah, I think an easy way to show superelasticity is, in fact, to look at this diagram, and I would say that I'm indebted to Bob Cousy, my colleague on the faculty, who's a mechanical engineer, for helping me understand these things. If we look at this rather complicated graph, what we have is a stress-strain diagram, and what it's showing is what happens when you bend a piece of superelastic wire. Let's imagine that we take a piece of superelastic wire. It's supplied in the austenite form, and it's relatively stiff initially. As we bend it, it has a linear portion, and then at a certain point we hit a shoulder. And what happens is, at this point, we begin to induce the formation of martensitic nickel titanium within the austenite. And as that phase transition occurs, the wire bends, but the force doesn't go up. At point C over here, all the austenite has become martensite. And now we're looking again at a portion of a curve that looks just like that traditional force deflection or stress strain diagram. It's got a shoulder. We're not here far enough, it would break. If we let it straighten itself out, it does another interesting trick, and that is it doesn't retrace its steps along that original curve. Instead, it goes down to here, and at this point marked F, we get a reverse transformation. Our martensite turns back into austenite, and once again we get a very linear portion of this force deflection curve, and then finally it goes back to almost where it started from. Now, what that does, of course, is give you quite a distance along here where the force delivered by a wire would be almost independent of how far you bent it, and that's the magic trick in orthodontics. What we would like, of course, is to be able to tie crooked teeth into an arch wire, and it wouldn't matter really how crooked they were. The wire would deliver the right force to pull them back into place. We can look at another diagram that lets us compare stainless steel, which is this part of the diagram. This is just a traditional force deflection diagram. You can see that the steel bent way out here. It didn't spring back terribly far. We bent it out of shape really badly to bend it that far. Nitinol is the original martensitic nickel titanium wire, and it's an elastic material. You can see that it bends much better than stainless steel and springs back a whole lot further. What's labeled as Chinese Nitai here, because that was the first version of it that was in the scientific literature. The Chinese Nitai is super elastic, and here you see this incredibly flat force deflection curve with this incredible recovery. It was bent 80 degrees, and it sprang back almost totally, and it delivered that very nice, almost constant force over quite a considerable distance.
Now, based on that diagram, or the two diagrams that we just saw, what's the relationship or a comparison with the superelastic Nitai and the stainless steel? Before I talked about like the difference between an 016 and an 018 wire. How does that fit in here?
Well, you see, if it's an elastic material, the size of the wire is critical, because as you change the size of the wire, you greatly change its properties. But if it's a superelastic wire, it's a different ballgame. The manufacturer can give you almost any spring properties you want, and they aren't totally independent of the size, but they almost are. So the manufacturer could make you an 016 that was stiffer than the 018 if he wanted to. And now you have to look at the amount of force that the wire will deliver and choose your wire based on that, not based on its size. It makes sense often to use an 016 size, and you'd need to if you were using an 18-slot appliance. If you're using a 22-slot appliance, you could amuse yourself, I guess, and get an 18 or a 19 or any size you wanted to almost, so long as the manufacturer gave you the properties you wanted.
Now, if someone's at the annual meeting of the American Association of Orthodontists and they see in the commercial exhibits Nitai wires of various sorts, how does someone make an intelligent decision about what to buy?
Well, first thing you do is you say to the salesman, is this stuff M Nitai or A Nitai? And if he gets this puzzled look on his face, you say, see you later, Jack.
Okay, now
and you go somewhere else.
Obviously, the martensitic Nitai is. Yeah. Now, what is it exactly that you want to, and what is the question you want to ask him if he does know the difference?
Well, I mean, all Nitai is not super elastic. That's the point. You know, if you want super elastic Nitai, you want an austenitic nickel titanium that will undergo this phase transition under stress to martensite. And you really are at the manufacturer's mercy. You know, there's stuff being sold to orthodontists that I'm not at all convinced it's what they said it was. And I would only buy super elastic wire from somebody that I knew for a fact was really honest to God selling super elastic wire.
Okay. Now, one of the drawbacks of most of the, or I guess almost all the nickel titaniums, is the issue of formability. How possible is it to bend let's say a super elastic Nitai? Is it possible at all?
It's not impossible, but gee, it's difficult. You know, you work really hard to bend it, and you put a bend in the wire, and it looks like you put a bend in the wire, and then you can stand there and watch it disappear over the next minute or two. You really use super elastic wires of that type at a stage in treatment when little details of wire shape aren't that important. These are for gross early movements. And so, you know, it's just a matter of getting an arch form that is reasonably close to what you want for the patient and figuring that you're going to replace this superelastic material with something else down the road. You can't do all of treatment with the superelastic wire, but gee, it's nice for the initial phase.
Sure. Well, that actually brings us to the next and almost final topic that we'll consider, and that is the sequence of arch wires and how they're used. You know, everything from initial leveling and aligning of teeth to the finishing. You want to go through sort of maybe philosophically a little bit about which wires you would pick for which purposes?
Well, first of all, it's important whether you're using 18 or 22 slot because the sequence of wires would not be the same with the two things. Remember, in an initial wire, you want an undersized wire relative to the slot so it can slide. Right now, there are companies that are pushing the idea you should put in a full dimension arch wire, very first thing in treatment. Makes absolutely no sense because the teeth can't get straight unless they move relative to the arch wire, fill the slot, getting in your own way. So it wants to be undersized. So it shouldn't be bigger than 16 thousandths, in my view, that initial wire in an 18 slot appliance. You could put a 16 or an 18 or I guess even an 020 in a 22 slot appliance. But that first wire wants to be undersized. The 16 thousandths superelastic or austenitic niti is an ideal first wire, but it does have a disadvantage. It's expensive. And so if the teeth aren't terribly crooked and you want to use something less expensive, you could use a multi-stranded steel wire. And in the multi-stranded steel wires, the one that's 3 strands of 008, which is 0.0175, is the one with the best properties. So if you're a 22 slot person, that's great. If you're an 18 slot person already, that's a bit of a problem because it's too big relative to the slot. If you're an 18 slot orthodontist, you really need that 16 thousandth superelastic wire. If you're a 22 slot person, sometimes you can get by with a less expensive multi-stranded steel in a way you couldn't with 18 slot. Start with 16 niti. Then you're going to want to level the arch after the initial alignment, and usually a stainless steel wire does that best, still a round stainless steel wire, typically 16, sometimes 18 thousandths. 18, of course, again, would be better in a 22 slot appliance than it would in 16. You're then perhaps going to be closing space in an extraction case. Perhaps you're going to be correcting the molar relationship in a non-extraction case. And it's going to depend really on how you would do those things. In an 18 slot appliance, once the teeth are aligned, filling the bracket slot becomes an advantage. So 17 by 25 beta titanium is often an excellent wire to follow the 16 steel. And with the 18 slot appliance, one of the reasons you're using it presumably is so you can finish with a 1725 steel wire, and that's an excellent finishing wire. In the 22 slot appliance, if you're going to slide teeth to close space, then you might use an undersized steel wire. 1925 steel is good for sliding extraction spaces closed, for instance. But eventually you're going to need to fill the bracket slot in order to get the case finished. And so large dimension nickel titanium, 21 by 25 nickel titanium, for instance, is a good wire to use. And now you really want the elastic one, not the super elastic one at that stage. 2125 beta titanium is a beautiful finishing wire in 22 slot, and you wouldn't finish with a steel wire. So the sequence of wires would depend on slot size, and it would also depend on what you're trying to do.
Now, you have not, in the discussion that you just had, you didn't really talk about any rectangular superelastic wires.
I don't have any use for rectangular superelastic wires.
Those are used not at all. In other words, that's when you'd be getting into the beta titanium sequencing.
Or I might want the elastic nickel titanium. If in a 22 slot case I wanted to do some initial torque and those kinds of things. I'd be happier with the elastic rather than the super elastic version. There's a place for everything. Super elastic wires are great when they're small and round and undersized, and as they start filling the bracket slot, I no longer see an advantage.
Okay. Now, are there any other comments about Archwire selection that you want to make? I want to finish this up by talking about where you think things will be 5 or 10 years from now. Are there any other specific technical aspects regarding wire selection that you might want to talk about?
Well, clearly we haven't covered everything about a complex subject.
No, I understand
but, you know, we've, I hope, given a good broad outline.
You mentioned before that you felt that orthodontics was following the aerospace industry by 10 or 15 years.
Yeah.
And what do you see on the horizon that doesn't exist now, at least as an everyday product that might exist in the future?
I think it's really very clear what's going to happen, and you can see it in two ways. My son is an Air Force fighter pilot, and he flies, or rather flew very proudly, the F-15, which is our state-of-the-art fighter plane. It's a titanium airplane. He recently gave up his F-15 for a desk job. He's now working in the F-22 program to build the fighter of the 21st century. And it's a plastic airplane. It'll be composite plastics. All the new high-performance stuff is composite plastics. I have seen the first beams, the size that would go in orthodontic brackets, that are composite plastics. The experiments are being done right now, and I'm sure that in the year 20-something, you know, Dr. McNamara is going to be asking his nurse for a beam of a certain size, because it won't be wire anymore. It'll be some crazy kind of plastic.
You think that that'll be true for the brackets as well?
Probably, almost certainly. You know, stainless steel will be as obsolete for orthodontic purposes in a few years as gold is now.
Are there any other comments you want to make on this subject?
Well, Jim, it's kind of fun to be up at Michigan. It'll be interesting to see what your students think of this.
That's right. Bill, as I mentioned before, gave the Juraback lecture, the first one, in 1985. And his presentation at that time was perhaps one of the clearest I had ever heard up to that point, and even to this day, regarding the issue of archwires and a lot of the new materials. You've always seemed to keep right on the forefront of this topic, and I greatly appreciate you spending time with us today. Thank you.
Thank you.
You've been listening to a presentation from the University of Michigan School of Dentistry, which is dedicated to supporting open learning and open educational resources. This recording is licensed under the Creative Commons. It may be reused and redistributed for nonprofit use. Please attribute materials to the University of Michigan School of Dentistry and redistribute under this same license. For more information on how this and other University of Michigan School of Dentistry recordings may be used, visit www.dent.umich.edu/license.